Hi everyone. In this video, we're going to talk about halogenoalkanes, about how to produce halogenoalkanes, about types of reactions, how to produce, and let's discuss about the uses and impact of halogenoalkanes, also about halogenoalkanes reactions. So you can see these are the contents of this video. But I will divide this video into two sections, yeah, because otherwise it will be too long. Okay, so section 1 until content 1 until content 5, and then the last section and past paper practice questions will be at the second video. How to produce halogen alkene? Do you remember that free radical substitutions of alkene will produce a substance that called as halogen alkene? You know that if we have methane in the presence of Cl2 and UV light, it can undergo substitution reactions to form CH3Cl and HCl, right? The class of CH3Cl called as halogenoalkene. So the first way to produce halogenoalkene is by free radical substitutions of alkene with halogen in the presence of UV light. We already learned about alkene as well. Can you remember how to produce halogenoalkene from alkene? Yeah, you can use hydrogen halide, right? It can change to halogenoalkene. Okay, this is the second way of how to produce halogenoalkene. Yeah, it's by addition reaction, yeah, electrophilic addition of alkene by hydrogen halide. Okay, the third way, we will discuss about this at the next video. I mean about chapter 17. Yeah, it is from alcohol. For example, if I have ethanol, CH3CH2OH, we can change this to halogenoalkene. Okay, by nucleophilic substitutions of OH group. Yeah, there are 4 reagents that can be used to produce halogenoalkene from alcohol. Okay, it is PCl5 or SOCl2, or it can be PCl3 and concentrated HCl. Yeah, to produce halogenoalkene from alcohol. So there are 3 ways how to produce halogenoalkene. Once again, first is by alkene free radical substitution. Second, electrophilic additions of alkene. And then the third by nucleophilic substitutions of alcohol. What's the properties of halogenoalkene? First thing that you should know that halogenoalkene will not soluble in water. So it is insoluble, and the boiling point increases as the molecular mass increases, such as if you compare 1 chloropropane here, the boiling point is only 47, but 1 bromopropane 71, because the molecular mass increases. Boiling point also increases with the structure. Okay, I mean, if you have a straight chain, then you will have the greater boiling point compared than the branch one. Yeah. So for example, 1 bromobutane 101, while 2 bromobutane 91, while 2 bromo 2 methylpropene only 73. So the more branch, the lower the boiling point. So this is the physical properties of halogenoalkene. Yeah, solubility, insoluble in water, and the boiling point increases as the molar mass increases, also decreases if the branch increases. Okay, now we'd like to see about the polarity of halogenoalkane with carbon. You know that carbon and halogen atoms has difference in electronegativity. Okay, for example, CF, fluorine has a very high electronegativity, so it will tend to attract electron toward itself. So carbon that attaches directly with halogen atom will have positive partial charge. If we compare CF and CCl, then you can see that the polarity decreases. Yeah, since the electronegativity of Cl less compared than fluorine. So polarity decreases. And you can see as well what the bond length. You know that fluorine is smaller compared than chlorine, so the bond length of CCl is longer compared than CF. Since CCl longer, then to break the CCl bond needs less energy compared than to break CF bond. Okay, so you can see at the small picture here. Look here. Then the group polarity decreases, the bond energy also decreases. Yeah, once again, the bond energy is the energy needed to break covalent bond. Yeah. So if you compare about the rate of hydrolysis, of halogenoalkane, rate of hydrolysis, that means the times needs to break the CX bond by water molecule. Okay. Once again, to break the CX bond with water molecule that we call as hydrolysis, the rate of hydrolysis of chloroalkene is less compared than bromoalkene, and this is less compared than iodoalkene. So that means the faster halogenoalkene to undergo hydrolysis reaction is iodoalkene. Yeah, since the bond length very large, so just this a small amount of energy to break the bond. Okay, chloralkane actually is not reactive. Yeah, due to it is very small and very small in the bond length, so very high bond energy. Okay, so actually chloralkane is reactive. Okay, we already learned about the physical properties of halogenoalkanes, also about its reactivity. So now let's continue with this practice question. Please try to answer this first. Okay, what's the answer? The answer is C. Okay, why C? Okay, you can see that CFC such as CCl3F and CCl2F2 are more stable than chloroalkene. So you can see that the fluorine atom present in CCl3F or CCl2F2, which is 2 chlorine from CCl4 has been replaced, 1 or 2 fluorine from CCl4 has been replaced with fluorine. Yeah. And then the question states that this is more stable compared than CCl4. So that means the presence of fluorine affect the stability. Okay. Asking why? This is because of CF bond is very large, so needs very high energy to break it. Yeah, so that's why it is more stable compared than the chloroalkene. Okay, let's try to do this. Okay, the answer for this question is B. Why B? Okay, ethane and fluoromethane have the same number of electrons in the molecules, but their boiling point differ. Yeah, you know that once again, MR of these two compounds similar since it is stated that they have the same number of electrons but differ in boiling point. Why? This is due to CS3F is a polar molecule. Yeah, due to the presence of F, high electronegativity atom. So that's why it attracts electrons toward itself. Yeah, created negative partial and positive partial charge. This we call as permanent dipole, while alkene does not. Okay, why not C? Means CS3F also has a very strong bond, right? Yes, it is true. But does it affect the boiling point? How do you think? What is boiling point? Boiling point is the energy needed to break the intermolecular forces. So that means if we have one molecule and another molecule, we should break this bond, right? These intermolecular forces should be break. And these intermolecular forces depends on the type of bond, yeah, such as is it have a van der Waals forces or permanent dipole or hydrogen bonds, right? So interactions between two molecules, yeah, between molecules and molecules. But you can see that if you want to break the C and F bond, okay, if you want to break this is called as bond energy, and this is not about boiling point. Yeah, once again, this is when we want to break the CF bond. So that means we break the intramolecular forces, intramolecule bond. Okay, and this not affect the boiling point. Once again, boiling point is because intermolecular forces, not because of intramolecular forces. Okay. How do you think about T? Hydrogen bond occurs in CH3F, but not in CH3CH3. You can see that CH3F does not fulfill the requirement for hydrogen bonds to occur. What? Do you say what? Means hydrogen bonds form between H with FON, right? We have fluorine here. So, is it true that hydrogen bonds occur? Yes, this molecule has fluorine atom, but it doesn't have the positive partial charge hydrogen. So for hydrogen bonds to occur, yeah, the two requirements should be fulfilled. First, the molecule should have the positive partial hydrogen, and then the second, it should have lone pairs of electron from a very electronegative atoms such as F, O, or N. These two requirements should be fulfilled for the hydrogen bonds to occur. Okay, let's see if we have these two requirements. Okay, we have electron lone pair of electrons from F, yeah, a very high electronegativity atom. But do we have the positive partial each? No, because hydrogen attaches to carbon, which is not electronegative. So the carbon here will not have positive partial charge. So the second requirement does not fulfill. Okay, so hydrogen bonds does not occur in two CH3F molecules. So that's why the answer is B. Bravo. Okay, let's try one more. Okay, let's answer this. Properties of fluoroalkenes. They are less reactive than the corresponding chloro. Yes, is it true? It is true. Why? Because once again, fluorine, carbon fluorine has the shorter bond length compared than carbon chlorine. Yeah, they are non-flammable. Yes, it is true. Why? Because this molecule is unreactive and they are non-flammable. The CF bond is stronger. Yes, it is true. So A is the answer. Okay, so far we have learned about how to produce an halogenoalkane and the properties of halogenoalkanes. Okay, this is the third point that we will discuss here. It is about types of halogenoalkane. Okay, there are three types of halogenoalkanes, which is the primary, secondary, and tertiary. Look carefully. The primary halogenoalkane means the halogen atom bonded to carbon. Okay, once again, halogen atom bonded to carbon that bonded to one another carbon only. Okay, primary. While secondary, bromine attaches to the carbon that attaches to two another R groups, to another carbons. While tertiary, bromine attaches to carbon that attaches to three another carbon atoms or carbon groups. Okay, so once again, this is because of halogen attached to carbon that attaches to how many other carbons. So your focus should be at this carbon, okay? If this carbon attaches to one R group, the other hydrogen, so it is primary. If two, secondary. If three, tertiary. Okay, the reactivity of halogenoalkanes depends on the types, or is it a primary, secondary, or tertiary? Okay, let's start to answer this. Which formula is that of a secondary halogenoalkane? Okay, it is very clear, right? The secondary is B. Okay, you can change it to the display formula, yeah, to make this clearer. So this is secondary. Why? Because bromine attaches to carbon that attaches to two another carbon atoms. A is primary. C is primary as well, right? And D is tertiary. Okay. Let's answer this. Okay. The Finkelstein reaction occurs when NaI in propanol reacts with a chloroalkene or bromoalkene, and the halogen is directly replaced by I. The reaction only works for primary halogenoalkane. Which halogen alkane produces compound X? Okay, you can see the carbon-carbon chain, yeah, the carbon-carbon chains in X, and compare with the options. Okay, let's see whether we have A or not. Okay, for the answer. Okay, CS3 2 times CH, yeah. This CS3 2 times CH, and then CH again. Yeah, look here, we are here now. CH connected to CS3, and then CS2, CS2Br. Okay, in the presence of NaI, once again, Br will be replaced by I. Okay, is it true A? No, it is wrong, right? You can see that this is I. Okay, let me use the green color. This is I. CS2 here. It should CS2 CS2 again, right? But in the structure of X, you can see that this is branch. Yeah, the metal group should be here. Should be here. So A is wrong. Okay, A is wrong. But B, okay, CS3 2 times CH, okay. CH, CS3, CS2, I, yeah, because we are replaced by I. Okay, but you can see that the number of carbon less compared than X, right? How do I know? Yeah, let's count. 1, 2, 3, 4, 5. Well, we just have 4 here. Okay, so different, right? So B is not the answer. How about C? Okay, let's do the same way. CS3 2 times CH, CS2, CS2, CH, CS3, Cl, and then Cl replaced by I. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The metal group at the, oh, that's wrong, not the first, yeah. Should be here. This is 1, 2, 3, 4, 5, 6. So there are 6 carbon as the longest chain. And that's wrong again, yeah, because it's supposed to be 5. So this is wrong. How about D? Yeah, the answer should be D because no more options, right? But let's check. Is it correct or not? CS3 2 times CH, okay? And then CS2, CH, CS3, CS2, Cl. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The metal group at the second and at the fourth carbon, right? The second and then the fourth. Okay, the second and then the fourth. So exactly same. Yeah. So which halogen produces compound X should be D.